This discussion, I am going to give you 3 things that I want you to be able to see and do. First, I want you to be able to map out what is happening in a problem. Sometimes you can do it through reason, sometimes you can't. This problem, I believe, you can map out. Second, you should be able to draw a velocity and a position graph that corresponds with the information presented. Third, you should be able to cut to the chase and use a Galilean motion equation to derive and calculate the answer. That's what you should be able to do by the end of the discussion today. I feel pretty confident we can get there. But I want to start with just thinking about the question and drawing myself a little picture about it. Fair enough? So here we go. In listening to the problem, it suggested that you threw a ball upwards in the air at 40 meters per second. That's a little squished. I will be less squished there. So 40 meters per second. After 1 second, how fast is the ball going? Yes, sir? 30 meters per second. Thank you. You had to do 2 things there to get the answer. First, you had to know the size of the acceleration, which they tell us is 10. Second, you had to know that the acceleration was acting downwards. Not an unreasonable thing for me to ask, but I want you to think about it. The acceleration is actually taking away some of the velocity. It acts downwards. Meaning at the end of this 1 second, the ball is now here, but traveling at 30 meters per second. Fair enough? I drew a shorter arrow. Is that not lost on you? That okay? In the next second, the ball loses some velocity again and is now traveling how fast? 20 meters per second. Because, as we might want to point out, there's an acceleration acting on the ball downwards at 10 meters per second. I'm trying to draw a red arrow that is the same size as the red arrow that I drew before because they're always 10 acting downwards, taking away velocity. And now my velocity is smaller yet again. That doesn't look that much smaller. Let me do better. There, smaller. 20 meters per second. How many seconds until the ball stops? What's that? 1 more, right? 4 total. Fair enough? 40, then 30, then 20, then 10, then 0. Any questions about that? We're trying to imagine that the ball will eventually reach a point where its velocity will be 0. So the truth is, the 40 should have been written right here, because after a second it's 30, and you get the point. I don't need to emphasize this much more. The idea is you should rationalize what's happening in the problem. Now, that being said, I do believe that you could, using this information, produce a reasonable graph of what happened to the object. And for this, I don't think you have to do very much. 4 seconds, 40 meters per second. How did I know to make this a straight line? That's an important question, actually, and one I'd lead you to know the answer to. I have 3 people who believe they have the answer, maybe 4 or 5. Let's start in the front. Yes, sir? You had your hand up first.
No more forces being added.
Oh, let's not use words I haven't brought up in class. Not to insult your intelligence. I want to use just the words we've used in class. Go ahead.
No more velocities being
Yes, sir?
The acceleration is constant.
The acceleration's constant. That's the exact words I wanted. I'm not trying to neglect what you said. I'm not saying what you said is wrong, but I want to use the words that we have in class. On a velocity, and this is actually stuff I want you to have to know on the next test. This is a velocity versus time graph. If I want full credit on the test, the axes should be labeled with units. I should at least hit proper points, but I should also know that this is broken down into even increments. My graph should start from 0 in both axes. These are things that all of our graphs should do. You should never start your graph away from 0. Always start your graphs at 0. If you want full credit on the test, that's the kind of thing I'll be looking for. We were told the acceleration was a constant at 10 meters per second squared. Therefore, this slope had to be a constant. You really need to come to grips with what the slope of each of these graphs means and what it means to be constant. It is easy to trip you up. So you need to be aware and thinking. As I said from the very beginning of the year, I will never ask you what the definition of a word is. My expectation is you understand the word enough to use it in context. The slope of the velocity versus time graph is the acceleration. The acceleration was told to us to be constant, so the slope of this line had to be constant. More importantly, I know the slope of this line is negative 10 meters per second per second. Has to be. I don't have to work out the slope. We already did. We were told it was negative 10. Questions to this point? Excellent. So, how high above me is the ball when it comes to rest? Now, I want to work it out, but who believes they know how to get to the answer? Maybe 2 people? Okay. I want to remind you from what we talked about yesterday that the area under the curve represents the displacement during that time interval. All of our graphs we should test for area and slope to see if they have meaning. At this point, I'm done asking that question. On a velocity versus time graph, the area under the curve is the displacement. So in this case, my displacement, which I'll write as delta x, equals 1/2 times the base, which is 4 seconds, times the height, which is 40. Suggesting that the ball is 80 meters above where I started. Sorry, it's come back, promise. 80 meters above where I started. So in the 4 seconds, the ball climbed 80 meters. Any questions about this? We doing okay? I'm going to push you into uncharted territory now. I would like you to sketch a position versus time graph for these same events. At time 0, and here's where you really should listen. At time 0, the velocity was 40. That means at time 0, looking at this graph, is the velocity ever the same number for any 2 seconds? I mean, at second 1, we already cleared that it's 30. And at second 2, it's 20. And at second 3, it's 10. Is there any 2 times where the velocity is constant? Which means there's never going to be a part of this graph the velocity's always changing. In fact, what is the velocity at t equals 4 seconds? 0. So, look at what we talked about yesterday. First, by definition, this is a straight line. Y equals mx plus b. What's graphed on the y-axis? Velocity. So, v equals mx plus b. Except what's x? What's graphed on the x-axis? Time. Great. What is the slope for a velocity graph? Acceleration. And y equals mx plus b, which one of those is slope? The m. What does b represent? In the case of here, it is the initial velocity. Excellent. Yes, this is exactly what I have pictured here. I'll just put an F here to indicate it's the final velocity over the interval. Are we okay so far? We were told that the ball had an initial velocity of 40 meters per second. We didn't know how long it was in the air, but we were told that it had an acceleration of 10 meters per second squared, indicated downward, so I'll put a negative sign. And I was supposed to find out when the object came to rest. Do you see what I'm doing? Are we okay with that so far? This, of course, would have told me that it came to rest after 4 seconds. Not a surprise. If I use what we talked about yesterday about trapezoids, do you remember our discussion about trapezoids yesterday? I left you at delta x equals 1/2 the initial velocity plus the final velocity times the time. Based on what I just discovered, that this is a 4-second interval. 1/2 times the initial velocity plus the final velocity times the time. That should give me my displacement. Half of 40 is 20 times 4, 80 meters. Everybody following along so far? Any questions about what I just did? All right, here's where we're going to question it a bit. Somebody, and I don't care who it is, pick any other of the homework questions. First one to talk is my favorite. Yes, ma'am. You're not talking.
Oh, me?
You had your hand up first. Keep going, just read it. I don't care which one you read, they're all the same.
Okay, the ball slowed from 6 meters per second. Oh, sorry, wrong one. Consider the ball from the previous examples rolled up the ramp at a speed of 6 meters per second instead of being caught at the top. It rolls back down until it is traveling at 8 meters per second in the opposite direction.
Okay. This problem is contingent on having successfully answered the prior question. I need something from the prior question that is consistent for this question. And the only thing I know of that's consistent from the prior question is the angle of the ramp, right? That's the one thing we know, it's the same ramp. Give me the acceleration you found in the prior example then. All right, so you're saying negative, so you're saying down the ramp is negative. So here's my ramp. The ball was rolled up it, and we're saying that direction is positive? So this is your choice. Yeah. Remember, arbitrary. So that means down the ramp is 8, and down the ramp is also 2. How long was the ball traveling, and where is the ball at the end of when you catch it? Is that basically the problem?
Yeah.
Do you guys see this so far? Now, here's what I really want you to pay attention to. This is worth the price of admission today. I don't need a graph. If the acceleration is constant, the graph of the slope will be a straight line, and this will be the description of that slope. Everybody follow what I just said. It's very important that you do, and I stumble over my words. If the acceleration is constant, the velocity graph will be a straight line. Y equals mx plus b. So, v equals at plus vi. You guys see where I came up with that? Also, if the acceleration is a constant, the graph will be a trapezoid. One version of it. Rectangle, true trapezoid, triangle, they're all the same. It'll be something like that, which means delta x equals 1/2 v initial plus v final times the time. Everybody follow that so far? No, nobody follows that yet? Are we okay with this so far? If you'll notice, I have 1, 2, 3, 4, 5 different independent variables. In any one of these equations, how many are present? 4. You'll notice this one is missing delta x. This one is missing a. You follow so far? You doing okay? Now, my recollection of algebra is that you can only solve an equation if you have one missing variable. That's my recollection of algebra. If I have 2 missing variables, I'll need to have at least 2 equations. 2 equations, 2 missing variables. Do you remember algebra now? This is an algebra exercise. This is not a physics exercise. In fact, if I look carefully, I will notice that all 4 of these appear in one of the relationships already. Do you notice that? Please say you do. Because I noticed the other equation, if I tried to use the other equation, I would be missing both time and delta x. I'd be unable to be successful using that unless I had found the time or delta x first. But I'm noticing that I could use this relationship to find the time. Doesn't matter what order I do these problems in, right? I do the order whatever is convenient for me. So I'm thinking -8 equals -2t plus 6. No graph. T is 7 seconds. I don't do algebra or arithmetic if I don't have to. If you need to see either, you should ask. I'd be happy to slow down. But -8 minus 6 is -14, divided by -2 is 7. I now have t, 7 seconds. I'm pretty sure I could find delta x, aren't you? I just got to pick the right couple things together. I see delta x equals 1/2 the initial velocity, 6, plus the final velocity, -8, times the time I just found, 7. 6 minus 8 is -2. Half of -2 is -1, giving me a delta x of -7 meters. This object is behind me 7 meters away. How are we doing? Easy or hard? All right. I think you guys are pretty smart. Let's do one final example, okay? Let's see if you can really use this. A rocket accelerates at 20 meters per second squared from rest. It does so for 5 seconds. How high does it go? And how fast is it going after 5 seconds? So I'll say again, a rocket accelerates upward at 20 meters per second squared. It starts from rest and accelerates for 5 seconds. How high is it after the 5 seconds? And how fast is it going after the 5 seconds? Now, I want to stop for just a minute. Every one of these problems is exactly the same. They sound like they're complicated maybe in the beginning, but you should always consider that if it's a motion problem where the acceleration is constant, then every one of these problems begins with these 5 things. And every one of these problems can use these 2 relationships. Now, I can't keep you, but you should have been able to listen to what I said and recognize what was given. It's your job now to figure out what's missing. We finish tomorrow. It'll take about 15 minutes. And I'm just going to ask you questions. And as I ask these questions, if it spurs you to make a change, make the change you need to make, but maybe jot some of it down. Does the object always stay in the positive direction? Does it ever turn around and come backwards so much that it goes behind where it started? Not in the observable opinion of what we've seen. 4 seconds, right? So when asked to make a graph representing position from velocity, or making a graph of velocity from position, we are only observing the same time interval. So my time interval should end at 4 seconds. Keep going. This is position. At time 0, what is the position of the object? It's the ground. Can we call the ground 0? Seems not unreasonable. We only know one other position from what we've talked about, and that position is 80 meters away from the origin. Where is it 80 meters away from the origin? I'm sorry, when is it 80 meters away from the origin?
4 seconds.
So let's assume that now all of you understand where those 2 points came from. Actually, let's assume that you understand from where those 2 points came. You shouldn't end your sentence with a preposition that makes you sound unintelligent. I don't like to do that. So our next job is to connect these 2 points. We have 2 points to connect here. And I remember from last week that the slope of a position versus time graph is the velocity. That's an important detail, one I don't want to forget. Because if I connect this with a straight line, that suggests the velocity was always constant. Was the velocity always constant? No. So the 15 or so of you that have a straight line here, sorry you wrote in pen, you might want to make a change. Because when I look back, the slope of my position graph has to have a slope of 40. Now, I really don't have a whole lot to go on, but 40 is positive and steep. So I made a positive, steep little dash to remind me that my graph has a positive, steep slope at time 0, because the slope of a position versus time graph is velocity. Let's go back, where it's a straight line, because there's never a time where the slope is constant. The slope is always changing, because the slope at 4 seconds has to be 0, flat. I need to draw a function that starts steep and becomes flat. I don't have to know what that function is. To sketch a graph, just need a sketch. That's not a great sketch, but it'll be okay. It's a curved line. Tells me that my velocity is always getting less until it's finally 0. How do we do? Based on what I saw out there, there was some people who could not start, some people who started but didn't draw a line or anything. There were some people who drew a straight line connecting these exact 2 points, and there were a couple of people who had enough intuition to draw the curved line. All 4 of you exist in this room. I need all of you to be in the last category by the end of the class period today. Okay? So if you'll remember, I said I wanted you to learn 2 different things. I want you to be able to work out in your head what's happening, maybe draw yourself a picture of what's happening. I want you to be able to graph what is happening. We've done the first 2. The third one is I want to extrapolate from the graphs to a manner in which we can just use a relationship to find our answer. That's what I want to do now. Ready to move on with that? This requires that we take